the frequency domain problem. We'll cover the frequency analysis today. Okay, again, I repeat from last time, short time Fourier analysis, right? So speech signals, we always start with short time. So we talked about cutting the windows. Now we're processing the time domain. Now we're talking about it processing into frequency domain. So basically, Fourier analysis is a mathematical set of tools trying to understand or represent the signals by sums of sinusoids and complex exponential. Okay, so the idea is that why people want to do this is, usually it has a better insight into the signal properties, because people like to know, okay, what are the frequency component of the signal, okay? Is it oscillating at a particular frequency, okay? What kind of, oscillation is happening in this time series signal stuff. So by taking the time domain signal into a Fourier domain, it helps us to start understanding that, okay? And also, we know from a signal and system perspective, you're designing filters, you're designing systems that try to change some parts of the frequency responses of your signal, and you can understand the response properties better from the Fourier analysis perspective, right? So you can think about this response as a superposition of sinusoids. If you want to kill off a high frequency, right, because there may be more noise there, then you're designing a low pass filter, right? If you want a particular set of frequency you're interested in, okay, in your speech signal, you design those band pass filter or those frequency band filters. So from a system signal perspective, it's easier to understand whatever system that you're trying to design to process this set of signals. Okay, so in short time concept, right, we always assume there's a short time stationary assumption. Meaning within a small segment of window, the properties of the frequency don't change. Okay, though you do Fourier analysis, it makes sense. Okay. If you look at the too wide of the window, because the frequency content may already change, so the Fourier analysis may not fully represent what's happening. Okay, so let's look at the definitions. Let's look at definitions, right? So x of n, right? That's the index of which audio frame we're looking at. E to j omega equals summations of the windowed audio segment, right, multiplied by e to minus j omega. Okay. So you can think about short time or time dependent Fourier transform is just really the Fourier transform of a segment of a signal. Or we can look at this form and start rewriting this. Okay, do some change of variables by taking n minus n equals to another variable called n. You can rewrite this now become summations from n minus infinity. Okay. Xn minus m e to the minus j omega n minus m, right? They become two signals multiply each other. It's just that this one has been flipped and shifted, right? So this particular time-dependent Fourier transform can also be seen as the windowing function, the signal convolving with the signal called xn multiplied by e to the minus j omega n. Okay, so time-dependent Fourier transform can either be interpreted as a short windowed segments is Fourier transform, okay, or it can be interpreted as the window signal, okay, convolving with the original time domain signal. You just need to multiply by e to the minus j omega n. Okay, so these two are mathematically equivalent. It depends on whether you interpret the mathematical equation from the aspects of transform or from the aspects of system and LTI system convolution. Okay, so the signal can be either xn e to j omega, time dependent Fourier transform. Continue. Some since this is Fourier transform, let's look at some simple mathematical properties. Does it exist? Windowing means it's finite length. The finite length means in the Fourier transform of a signal of a finite length is absolutely summable. Always Fourier transform exists. So short time or short term Fourier transform always exists. Okay. Let's look at the form xn e to the j omega. Of course, this is a Fourier transform, so it's complex. It's periodic with 2 pi. Okay, this is the same thing with DTFT, right? This discrete time Fourier transform. It's just now we have a short window segment that you do a Fourier transform on. So xn e to j omega can be either written as rectangular form or polar form. The rectangular form is just the real part and the imaginary part, or you can rewrite them as the magnitude times some phase. Okay, so similar for all kind of imaginary signal. Okay, so if the signal is real, like speech signal, any real world signal. Okay, so any real world signal you can measure, they're always real signal. Okay. If the signal is real, this an omega, the real part of the Fourier transform, okay, is even, right? So an omega equals an minus omega. Okay. Bn omega will equals to minus bn minus omega. So the magnitude itself, okay, is again a even function. The phase itself similarly is minus theta n minus omega. You should be able to show this property fairly easily. They have the same property as discrete time Fourier transform. Okay, and then repeat. Many properties that short time Fourier transform shares the same property with the DTFT. Okay, linearity. If you have a signal that's a superposition of two signals, the Fourier transform of those signals equals to individual segments Fourier transform. Okay. A shifting in the original signal when you're trying to find the short time Fourier transform, this thing is just the shifting x of n minus n omega. By shifting that, you add e to the minus j omega not n. Scaling, okay, if you have a constant that scales the original time domain signal, you have the same scale, okay, in the linear in the frequency domain. Weighting, if you multiply the signal with some decaying function, okay, some constant multiplied by n, right? So it's some decaying function, or non-decaying function, as long as this is absolutely summable in that segment. Then this multiplication of this series equals to the scaling of your variable of a to the minus 1 e to j omega. Okay. Conjugate symmetry for real data, if x of n equals real, then xn e to j omega equals to xn conjugate e to a minus j omega. It should be equal to each other. Okay, these are standard Fourier transform property. Again, you should be able to prove them fairly easy. Okay, because everything is the same except you have a w and there in the term, which doesn't change the properties of all this property that you know with the Fourier transform. Okay, short time power density. Okay, so the power distribution over different frequency components, sometimes we call it variances, which Sn e to a j omega defined as xn e to a j omega multiplied by xn conjugate e to a minus j omega, right? Is trying to see the kind of the power over all the omegas, right? So it's Sn e to j omega. We can show that, right? This is equals to magnitude e to the minus j omega to the square, okay? Because the imaginary part will cancel each other out. Okay. From when you multiply the conjugate of its original signal, it becomes the magnitude to the square. Again, I'll skip this part, try to prove it at home. Okay, this x of n e to j omega, this n squared equals a Fourier transform of autocorrelation function of the original signal. Okay, so we know the short-term autocorrelation function is a function that measures the similarity across the same across your signal within that short segment. The power density function of that short segment of signal equals the Fourier transform of your autocorrelation function. Okay, so again, so that's also another property you should keep in mind. Okay. All right, these are some properties you can easily prove by just deriving through the equation. Many of them are very similar to the original Fourier transform. Let's look at some interpretation. Quite important. So we know xn e to j omega, right? It's short time. Okay, short time Fourier transform, right? Equals right short time Fourier transform. So you multiply the signal to a windowing function. Okay. Now let's define some terms. Let's look at w e to j omega, which is the Fourier transform of your windowing function. Okay, if it's rectangular, it's the same function, right? So basically, minus m to infinity w n e minus j omega n. Okay. So now term x e to j omega, which is the Fourier transform on the original signal, and this is that form. Okay. So now xn e to j omega equals to Fourier transform of this signal multiplied by this signal, right? Fourier transform this signal multiplied by this signal means Fourier transform of this signal, right, convolving with this signal. Okay, because that multiplication into the Fourier transform becomes a convolution. I should push this Fourier transform within the multiplication. Okay, the multiplication becomes a convolution. Okay, so the convolution becomes the multiplication. Depends on which way you're going. Okay, so taking the Fourier transform of the convolution becomes multiplication. Taking the Fourier transform of the convolution, it becomes a multiplication. It becomes a convolution. So you have Fourier transform of Wn minus m convolving with Fourier transform of xn. We know this, right? It's a shifted sequence, so it's just the e to a minus j omega n and the Fourier transform of the windowing function convolving with the original signal's Fourier transform. Okay, so the short time, okay, Fourier transform equals to the windowing function with this e to imaginary omega convolving with the x to e to j omega. Okay, you can rewrite this thing also as this two things convolving with each other. Alright, so I'll make this thing. So Fourier transform of xn convolving with the Fourier transform of the shifted window sequence. We can then think about that as time. This time dependent xn into a j omega can be viewed as a called smooth or window filtered Fourier transform of the signal within that window. Right? So again, this is the time dependent Fourier transform. Okay, this is the original x signal's Fourier transform. It's convolved, basically being filtered by the w e to the j omega. Okay, so it's somehow somewhat being smoothed or somewhat being filtered, okay, by the windowing functions Fourier transform. Okay, by windowing functions impulse responses. Okay, so the windowing function smooth out or filter out, okay, x to e to the j omega to get the actual x and e to the j omega. So again, repeat. Okay, your signal originally is xn, right? That's the signal you want to try to analyze. But you can't analyze because it's too long, okay, non-stationary. You make a short time stationary assumption by taking a small segment out. Take that small segment out, and then you perform Fourier transform. The Fourier transform you get is we call time-dependent Fourier transform. That actually means the original signal's Fourier transform multiplied by some, not multiplied, convolving with the Fourier transform of the window function. Okay, so the final response that you get here, the Fourier transform here is this two things that's convolving each other. Okay, just keep this in mind. So once you have this, right, you probably see now why we kind of start talking about last time. Okay, it's also important here. It's important to talk about the properties of the windowing function. Okay, because the short time domain signal, the short time dependent Fourier transform equals to your signal multiplied by the window of your choice. That choice is Fourier response. Okay, so that kind of conclusion changes the things. Okay. All right, so we hope W e to j omega. Okay, the ideal case is hopefully is like an impulse response in a frequency domain, right? Delta omega. Right? So the convolution provides the most faithful reproduction of the original x e to j omega. Assuming right x and e to a j omega is the thing you finally get, right? Take a short segment out, do Fourier analysis. Okay, you're getting this. Effectively, you're getting this. Okay. So if we can choose which windowing function you use, hopefully you want to choose this as delta function. Because delta function convolving with your signal, repeat its own signal. Okay, so that doesn't change what the x e to j omega is. Okay, that's the best ideal w e to the j omega, that windowing function you can choose. If you can choose that w e to the j omega equals some delta function, then this convolution will not change your signal's property. Okay. So that would be the best ideal case, okay, for choosing W e to j omega. Of course, that's ideal, mathematically ideal. We know practically that's impossible, right? So a window always has a finite bandwidth. It can't be a true, okay, delta function, right? Delta function meaning at some point it shoots up to infinity, okay, with infinitesimal width, okay, it shoots up to infinity at zero. Everything else is zero. It's just infinity, everything else is zero. Okay, so that delta function is not implementable. We know true delta function, okay, requires the other domain to have infinite length signal. Okay, a delta function here, or a delta function in the frequency domain means in the time domain signal is infinite length. Okay, to have a delta function in the time domain signal, it's the same thing. The Fourier domain you have a complete flat spectrum. Okay, so you cannot have a true delta omega as your windowing function of your choice. So you cannot say, okay, let's design delta omega and then try to do inverse, trying to find what the windowing function is. But in that case, it can't be. I mean, it's intuitive, right? To be completely faithful to the original signal you have, right? In a time domain signal, you just get everything, right? It's infinite in length. Okay, so no, you cannot get that because you're doing a short-term processing. Once you do a short-term processing, you can no longer get the original signals for your transform. Okay, so that's mathematically tells you, yes, in theory it works, in practice never gonna work, okay? Because it becomes trivial nonsense, right? To get the original x(2j omega, just look at everything. But the problem is you can't look at everything. That's why you do a short-time processing. So the idea then become, engineering. We try to solve this problem by, okay, now we still have to do short-time processing. How do we choose that functions of windowing so that when we do this convolution, it has minimally impact on the original x(2j omega. All right, so that's idea. Okay, in practice, there are two things you can design. You get have caught up. This metric in the signal usually will look something like this. Okay, the WE to the J omega. You have some like delta function thing, but it has a bandwidth. Okay, so we call this main lobe. And this main lobe width, okay, gonna be inversely proportional to the length of the window. Okay, for all window, it's the same. Okay, the longer the window, the narrower this bandwidth. Okay, again, same thing. As you look at your time domain signal more and more and more, you are more precise on what frequency you have in your original signal. Okay, the shorter you read, right? Then we get wider. Okay, so when you do this thing convolving with your original signals, okay, anything that falls in between here cannot be resolved. Okay, they all are coming from the same peak. Okay, so you lose that resolution. Okay, the longer you look at, right, then of course you have more peaky or more precise frequency resolution. Okay, side lobe attenuation, what we call side lobe attenuation is here. Okay, as you multiply, as you convolving this with your original signal. Okay, at the zero position, this is good. Okay, this is where we think there's a frequency. Then you multiply by this signal and tells you, okay, which frequency has what signal. But here, all these parts, they also have energy. Okay, it's not just completely zero. Okay, so this will also multiply to your original signal, and as though there's some energy that appears here. Okay, we call this side lobe problem. If the side lobe is large, if it's too large, then it cannot differentiate between the main lobe and side lobe. Okay, then you don't know which frequency is real frequency. Is it the one that originally exists in the original signal, or is it the one that's being introduced by the windowing function? Okay, right. So we want this side lobe level to be as low as possible. Even if you add a little bit sort of a nonsense frequency into your signal, you still add to a point that's low enough so you can kind of safely record them. Okay, so this we call a side lobe attenuation. We have to design windowing function such that hopefully this thing is as low as possible, this thing as peaky as possible. That means the main lobe width is as small as possible. Okay. All right, so the ideal thing is, since we cannot get the true delta function, okay, we hopefully will pick a window that has narrow main lobe and a small side lobe peak. Okay, again, really the idea you have to come from. Think about this process, right? X and e to the j omega, right? The Fourier transform of a short window segment equals to the Fourier transform of the original signal convolving with the windowing functions Fourier transform. Okay, you want this to be as faithful as to this one. Okay, without changing too much of this original property. Hopefully, this thing is small in bandwidth, low in side lobe. Okay, so we can look at several common window function, and then also there eventually tell you what are the go-to ones that people look like. So the most common one we call the rectangular window. Okay, it's also very straightforward. Okay, basically, intuitive is taking a short segment out, meaning applying a window function. That if you take n sample out, that means there's a window that only has value between 0 to n, okay, and then value 1, rest of it 0, right? So a rectangular windowing function can be written mathematically as w1 equals to un minus minus n, right? It's shifted n points, and this minus that, so everything else 0 is set for 0 to n. Okay, so and that part is 1. That's this regular windowing function. Okay, so if this is the windowing function you use, again, we can find the Fourier transform of this thing. Okay, and then I'll skip the steps. Okay, eventually it comes down to this form: sine of wn, capital N divided by 2, divided by sine w divided by 2. Okay, so the first thing, the magnitude at the main lobe, right? So then put omega equal to 0. Okay, so at the 0th frequency, at where the peak is, right? The amplitude here is at n. Okay, the first node, okay, which position of the frequency, okay, it'll give you the first magnitude equals to 0 is basically at every 2 pi over n. Okay, at every 2 pi over n, okay, omega every 2 pi over n, this windowing function's Fourier transform will has 0 value. Okay, so yeah, that's where the first node is. When you have the first node, then you know the main lobe width. Okay, that's basically 4 pi by n. Okay, so again, this is 2 pi n where it hits at 0. Then 4 pi divided by n, that's your main lobe width. Very easy. So finding the Fourier transform of windowing function, what is magnitude? Okay, find where the peak is. Find where the first point that this thing goes to 0. They are all symmetric. Okay, then you can quickly find out the main lobe width of this particular windowing function. And look at it, depends on n. Okay, n is your segment length. Okay, the larger it is, the main lobe width is going to be shrinking. Okay, the smaller it is, then the main lobe width will be wider and wider. Okay. First side lobe loss. Okay, let's look at this point and this point, right? So W1 e to the j 2 pi n divided by W1 e to the 0. Okay, look at this peak and at this peak. Okay, the difference between the two. Okay, and then basically you do some computation. It's about minus 13 dB loss. Okay, and again, so on to the rest of the stuff. Okay, so the first the first peak, the main peak versus the first peak. Okay, they're about 13 dB loss of the energy. Okay, is that good enough? We don't know. Okay, hopefully this can be evened out. Okay, the main lobe width is 4 pi divided by n. Okay, is it good enough? Okay, again, it depends on your application. Okay, but it'll also depend on the windowing segment that you choose. Okay. The longer the n, the narrower is the main lobe. Okay. Of course, it gives you the good frequency resolution, but bad time resolution. The longer the window segment is, okay, you don't know when things change because you lost your frequency time resolution. But you actually can be quite precise on what are some of the frequency within that segment. If you get very short, you know when things change because the time segment is short. Okay, that's a good time resolution. But you kind of start losing the track of, okay, where precisely are the frequency going to occur in this time domain segment. Okay, so this is a trade-off. Okay. This is the properties of rectangular window. And for many applications, this first peak side lobe loss is not good enough. Okay, so that's why there's other designs of the windowing function that try to hopefully change this. Okay, make sure this thing is lower. So there are two other very common type of windowing function people use. Okay, called Hamming window or Hanning window. Okay, they're very similar in concept. Okay. They look something like this. First, this is Hamming window. So they look like shape like this. So the idea is not to have a clean cut one across your window. You let your signal value start to slowly increase until the point that's fairly low at the edge, at the boundary, and drop to 0. Okay. The original rectangular window function, it has a flat here and sudden drop to 0, right? So okay, so how do we design this kind of function? Okay, so basically by changing by multiplying by some cosine function. So W1 of n, okay, that's still your rectangular window. Multiply b beta 1 minus 2 beta 2 cosine alpha, and where alpha equals 2 pi divided by n minus 1. Okay, by doing simply this, you get either Hamming window or Hanning window by doing choice of beta 1 or beta 2. Okay, now we can have a frequency response on this thing, right? So W2 e to j omega, this Hamming or this decay kind of windowing function, W2 e to j omega equals to beta 1 W1 e to j omega, this rectangular windowing function multiplied by some constant, right? Minus beta 2 e to beta W1 e to j omega plus alpha minus beta 2 the rectangular function e to j w minus a. Okay, so again, what you're seeing here, right, is some weighting of your rectangular function minus some weighting of the rectangular function with a shift of the signal. Okay, with a shift of in a signal frequency, right? So what the key point here is, it's a very clever design, right? here is original rectangular functions frequency response. Okay, if we can somehow shift, okay, this sideways, right? Then this peak minus the shifted version, okay, this peak will get demolished. Okay, so the idea is trying to design this kind of, cosine, right? When you define a cosine, it's actually shifting your frequency response to a new frequency range in a frequency domain, right? So it's by shifting that frequency response of the rectangular window to the point where you want to minus that, okay, minus the response. So you have two peaks get minus, okay. So the side lobe, because of this effect, will get minus out, okay. So the side lobe will get much reduced, okay. That's the basic sort of design of this Hamming window and Henning. Okay, so Hamming window and Hamming window, they're only different by beta 1 or beta 2. Okay, so beta 1 is 0.5 for Hamming window, beta 2 0.25 for Hamming window, beta 1 is 0.54, beta 2 goes to 0.23. Okay, so main lobe width, okay, let's look at Hamming window. Okay, main lobe width, okay, main lobe height, okay, is 0.54 n, right? It's again, LB1 is n, right? So main lobe for the Hamming window and the peak position, okay, this position will be 0.54 n. The first node, because the first node is not expanded. If you look at the first node, happens at 4 pi divided by n. Okay, so that means the main lobe width is 8 pi divided by n. Okay, so compared to the rectangular window, okay, what happens here is you lost a little bit of your main lobe width. Okay, the main lobe width gets wider, the frequency resolution gets a little bit worse. But the good thing is if we look at the amplitude at the first peak outside of the main peak, the energy differences between the magnitude now becomes minus 41 dB loss. Okay, which is quite good. Okay, 41 dB loss now on the log scale, that's a quite of an energy drop, right? So you start to think, okay, then originally, right, you still now becomes a bit more peak. It's just that this peak has a bigger width. Okay, but the side lobe now has become much lower compared to the rectangular window, which is, yes, it has a peak right here, okay, but the side lobes you can see they are all still pretty high. Okay, so it depends on what you're trying to do. Okay, these two are different forms of window and function people use. For most part, okay, you see people like to use Hamming window, okay, for many of the speech processing, okay, speech analysis, speech features extraction, all those things that become standard toolbox that people do. The first thing they do a windowing function. That windowing function usually people means Hamming window. Okay, that's pretty much better go-to method for trying to allow speech technology. But if you have a signal that you are very sure, it is less noisy, but the precise identification of that pitch is very important, or periodicity is very important, rectangular window is still the one to do, okay, because it really has a narrow bandwidth. Narrow bandwidth will actually tells you, okay, there's really a peak here, like, at 400 hertz, okay, there's oscillation. Okay, and then rectangular window will better pick that up, okay, compared to Hamming window. Okay, but the Hamming window, the good thing is it doesn't have all this nonsense auxiliary sort of artificial signals that exist because of the windowing function introduced the side lobe information into the original signal. Okay, so there's a trade-off. Okay, you cannot get both. Okay, but in all practice, usually people do Hamming window, okay, over a rectangular window. Okay, so now you should be able to know a little bit about this concept of the choice of a windowing segment. Okay, because if you analyze them from the frequency and domain perspective, it changes the frequency response of the original signal by introducing additional layers of information. And that windowing function of choice, okay, the length, the type will decide the final property of the signal that you see. So again, what's important here to keep it in mind. Okay, the way I usually say, okay, when you fire up a toolbox, you run any tools and then try to feature extraction. It'll extract feature for you, okay, it's all good, okay. But what you probably need to understand the choice of the parameters you make will changes the signals information that you actually compute on. And what you see are the outputs. Okay, so you want to know, okay, if I were to choose rectangular function and then I continue on to the rest of the processing of the speech signal, you have to bear in mind you might introduce a lot of the silo information, but you're probably more precise in your periodicity extraction. Okay? If you choose, okay, Hamming window, okay, you're probably more confident that there are no weird signal too much in your weird frequency in your output, okay, of the features or the analysis that you do, but you lack a precise frequency resolution. Okay? So you just need to know the design of the parameter impact the actual properties and characteristics of the signal that you can see. Okay? I think those are more critical than the actual mathematical derivation. But if you look at mathematical derivation, it's also fairly easy. It's just an exercise of Fourier transform. It's a very, very simple exercise of Fourier transform and look at the frequency response of your windowing function. Okay. All right, so some note on the some note on the choice of the window. So the frequency resolution really depends on the length of the window. To resolve pitch, okay, pitch is what? Pitch is the source, right? Speech production, source and filter model, source excitation. For all those voice sound, you have opening and closing of your vocal cord that creates that vibration. That's your pitch. And harmonic, so that's called fundamental frequency harmonics. So those things are multiples of fundamental frequency also exist. Okay, those are what we call pitch. If you are trying to resolve pitch from this one-dimensional time signal, okay, your Mendel width should not exist. Okay, not a pi divided by n less than equal to 2 pi f not divided by fs for a Hamming window. Okay, and you forget this f not divided by fs is the digital frequency. So again, Mendel width shouldn't be too wide. Okay, that means your window length shouldn't be too small. Okay, you need to look at couple period, okay, to make sure you have enough of those energy at that peak where you can actually resolve. Okay. To resolve formants, okay, formants are the resonant frequency of your vocal tract. Okay, they tend to be much higher than your fundamental frequencies. Okay, the Mendel width should be wide enough. Okay, to smooth out the pitch peaks. Okay, so what you want is your Mendel width when it's wide, that means your segment is short. Okay, so if you look at a shorter segment, you are not quite able to resolve pitch. But what you're trying to get at is the formant structure, the resonant vocal tract structure of your signal. So you don't see enough of the pitch, then you can't resolve pitch. And the frequency there you see are more formant frequencies than resonant frequencies and those things. Okay, so imagine this thing window is a smoothing operation, right? Depending on which end you choose. Okay, so we'll show a few plots, but basically the idea is different end you pick. Okay, the speech signal will show different frequency structures. Okay, either that structure correspond more to the fundamental frequency in the source or pitch, or they show more structure like formant. Okay, the resonance of your vocal tract. Okay, it's just because by simply tuning the number n, okay, and your windowing function, then you choose it, then you see a completely different structure within your speech signal. Okay, the idea again, try to link it back to the speech production we talked about, source and filter model. Some periodic pulses exciting a water tube, creating a resonance that becomes the sound. And we record that sound, taking that sound and then do Fourier transform. And that Fourier transform, take a small segment versus a long segment, is going to see a different property of this source and filter excitation and filtering operation. So that's the whole concept. That's the reason we need to talk about signals and systems and then this Fourier analysis in terms of this class. Okay, it's not because of the signal system, it's more because the speech signal is generated that way. So if you